welcome to the new discussion, which is basically part 2 of SAR interferometry technique. Very briefly, first we will see this figure again, as earlier also while discussing microwave remote sensing, active microwave remote sensing, we discussed this figure, but very briefly I will bring that in SAR interferometry, these SAR signals basically, as also discussed, that they contain basically the amplitude and phase information, and this amplitude basically shows the strength of radar response, and phase is the fraction of one complete sine wave, which we are seeing here, one complete sine wave with cycle as a single SAR wavelength. So, when it completes, once complete sine wave is there, that becomes the our wavelength here that we are seeing here. And when this phase of the SAR image is determined basically primarily by the distance between the satellite's antenna and the ground targets. So, this phase is basically based on the how far the antenna is between the target and antenna. So, based on that it is discovered. Now, interferometric because if ground deformations has taken place, then there should be some phase difference. If no ground deformations have taken place, then we will not be seeing those differences. So, what we in interferogram or in SAR interferometry, what it exploits basically the phase difference between the two complex radar observations, through complex numbers analysis first. So, that you are having a pair in between the some changes might have occurred, and these changes will bring the phase difference between these two scenes, and that can be exploited to generate interferograms. And that of course, it has to be of the same area and taken from slightly different sensor position, because it is not possible all the time to have exact position of the sensor or platform in a space. So, even if there is a reasonable baseline, perpendicular baseline distance is there, it is not a problem. Still interferograms can be derived or can be extracted. And this extract distance information about the Earth's terrain. So, this way we can exploit the SAR interferometry. Now, when we combine the phase of these two images or a pair after co-registration, earlier also I mentioned that this co-registration is very important. If two scenes have been co-registered nicely, then these will produce good results. So, after this co-registration, interferograms can be generated where phase is highly correlated to the terrain topography. Generally, this is the situation that our phases are related with terrain topography, and deformation patterns then can be mapped, because if the phase shift to topography is removed from the interferograms, the difference between the resulting products will show surface deformation pattern. So, in SAR interferometry, what we do, first we also generate a digital elevation model using that pair of the same area, and that digital elevation model is then used to subtract from interferogram, and that is why this we say as differential interferometry or D-INSAR also. So, basically it is not purely a INSAR for ground deformation studies, it is basically D-INSAR. I will explain again that a pair is taken. First, a digital elevation model of the area is estimated or derived, and that digital elevation model is used later on to subtract from interferograms, and then you get a product which will have no effect of topography, or minimum effect of topography, and through this subtraction, and then the product is called differential interferometry or differential interferograms. Let me give you one example, which is one of the very beautiful example, ground deformation induced by an earthquake event which occurred on 26 December 2003 in Bam place name is Bam, Iran, and the magnitude was 6.6. A pair has been taken, and the one scene of 3rd December 2003 and another one of 11th February 2004. And this is of course the NVSat ASR data, and here the baseline difference was only of 14 meter, which is very good for driving such interferograms. And this NVSat data was employed, and this DINSAR interferogram was generated. As discussed in the previous discussion, that these fringes and color of these fringes, the changes in colors or pattern of these colors can be used to count number of fringes, one. Not only that, but we can also know whether there is a subsidence or upliftment due to that particular earthquake event. Like for example, if I get a fringe color pattern like cyan, yellow and magenta, then it is concluded that there is subsidence occurred between those two dates for which we are having a pair. And if magenta, yellow and cyan pattern is observed, then it is upliftment. Now the question would be from where I should count, from outside or inside. So it is counted from inside. So if I here start counting that I will get first these patterns, like for example here I am getting cyan, yellow and magenta, and here I am getting, if I start from there, that I am getting magenta, then yellow and then cyan. So that means the lower part has got upliftment, the upper part has got the subsidence, that we will see through a deformation map as well. Now these colored fringes, as you are seeing, they are basically representing the ground deformation in the line of sight. In the units, as also discussed, that the C band was used. So it has the 5.6 centimeter wavelength. Half the wavelength will represent, one fringe will represent half the wavelength. Why half? That we have already discussed in previous discussions. And this half wavelength is, so these number of fringes are counted and then multiply by half the wavelength, and you get the total information about the deformation. So the basically in the main contributions to interferometry phase is the possible ground deformation, that is delta S, affecting directly the sensor target travel path. So think that if between those two dates, when those two scenes were acquired, if some ground deformation has occurred, then that can be detected very easily. So the only the projection of the deformation which is occurring along the line of sight, LOS, that is delta S, LOS is appreciated by SAR system. It is not the real, it is not the real deformation which has taken place, but the deformation in the line of sight. Though by using further processing we can create exact deformation as well. Now this LOS, or line of sight displacement of half of wavelength, causes a full phase cycle. So that way, for example, this example we have seen little differently, that when no deformation is there, like in this one on the left image, then no fringes will be observed in interferogram. But if some gentle deformation has occurred, in this case is subsidence, this is the pattern which we will see. And if steep changes have occurred, we might see even two fringes, like here, the example here. So when we take this back again, this interferograms of this, now we can interpret that in which part of this interferogram the subsidence has occurred, in which part the upliftment has occurred between these two dates, and we know between these two dates one big earthquake has also occurred. So we can attribute very confidently that these ground deformations are because of that particular earthquake. Now, there is one coherency part I would like to also discuss. What you are seeing here, these speckle, black dots speckle, these are the incoherent areas within this and also on the edges in the southeast or in the southwest direction, in the edges also you are seeing black dots, clustered black dots. These are the built up areas, and because of that big earthquake, these buildings or houses got completely damaged, and because of that the coherency for these areas could not be achieved through this interferogram analysis. So, those areas will appear without any fringes, but the areas which had the good coherency are showing very clear cut fringes. This is one of the best examples of DINSAR or SAR interferometry technique for earthquake studies. This is the ground deformation which I was mentioning, that this top part here, then when we get this color pattern, the cyan, yellow and magenta, on the top part we get the subsidence, and reverse to this pattern is what we get the upliftment. So, the lower part of this area got uplifted by about 30 centimeter, and whereas the upper part, this green area, is subsided by 20 centimeter. So, what we can say, that total deformation which was induced by that BAM earthquake of 26 December 2003 between these two dates is about of 50 centimeter. Half a meter deformation has taken place. Some areas have gone down maximum by 30 centimeter, some areas have got uplifted some areas have gone down by 20 centimeters, some areas have got uplifted by 30 centimeter. So, that kind of deformation estimations are possible through DINSAR technique, which otherwise there are no other techniques which can give us such kind of accurate information about the deformation. So, this kind of deformation estimations have become nowadays more or less standard in almost each and every earthquake, because the data is now available, regular data is available, and people, once the earthquake occurred, people analyze. And of course, in this one, in deformation map, wherever the coherence was not there due to the damage to the houses or building or structures, those areas in deformation maps are seeing no changes. That means they are appearing as white. No changes in terms of because the coherency could not be achieved there. There are some other also examples of DINSAR technique which is detecting the land subsidence, and this example of course from the Kolkata city due to over withdrawal of groundwater. As you can see here that of course these kind of deformations are very slow as compared to earthquake induced deformations, and therefore very clear cut or multiple fringes may not be possible between these two dates. But nonetheless, the deformation of a millimeter estimated rate of subsidence during 1992 to 98 was between 5 millimeter to 6.5 millimeter. That kind of range of deformations have been observed between those 6 years. So, this kind of the DINSAR or SAR interferometry technique can be employed where deformations have occurred between just two successive overpasses like in earthquakes, or there might be deformations which are very slow, like in case of subsidence due to maybe groundwater, subsidence due to mines, or maybe some landslide activities in the mountainous regions. So, there these things can really very accurately, unbiasedly can estimate the deformations which are taking place. Now, I bring another example from earthquake and which has occurred in Nepal, and there are basically two earthquakes have occurred. One is occurred on 25th of April 2015, another one occurred on the 12th of May 2015. and see the fringes which you are seeing, very close fringes in a small area were observed. This data analysis for this interferograms, ALOS pulsar data was used, and not NVSat, or of course NVSat is no more data available, neither Sentinel. So, ALOS pulsar data was used, and this product was generated by agency of Japan, a space agency, which is JAXA. So, here we can clearly estimate how much deformation and where deformations have taken place induced by these two earthquakes. That kind of accuracy cannot be achieved by any other method except in this through SAR interferometry technique. Now, there is another technique which is also now available, which is the basically you can say the next step in DINSAR or SAR interferometry or INSAR, that is the persistent scatterer interferometry, or in short we call as PSI. So, basically this is a branch of interferometry and that exploits the point scatterers. Instead of looking for the fringes, here individual points are used. So, point scatterers are exploited with a strong radar backscatter, which may be giving better or a strong backscattering over a long time period. That long time period might be years, because lot of data is available, successive data is available, and then if we employ this technique through these strong radar backscatterer for a long period, then we can know the history of that point target over time, how it has behaved. And this is not I am talking of one point. In one area there might be hundreds of such strong radar backscatters, and that can give us say ground deformations or deformations have taken place between that time period. So, as it says the persistent scatterer, that means that those point scatterers continuously are giving the backscattering, that too quite strong backscattering. You can say that something like a corner kind of reflector, which always are giving a strong backscatterer. So, these objects are identified or these points are identified through the analysis of several scenes of the same area over a long time period, and then point scatterers are identified, and based on that we can estimate how much deformations have taken place. So, persistent scatterers can be small in numbers, usually man-made features that remain very correlated over time. That is the one condition. If in an area I am getting just one or two persistent scatterers, then results I cannot have confidence in them. But if I am having multiple and these scatterers, then I will have lot of confidence. Though the conventional, why this technique sometimes is found better, because conventional DINSAR can have limitations with respect to discrimination between the effect of displacement and atmospheric signatures, because between those two dates a lot of atmospheric conditions might change, and though we are using long waves, generally these should not affect should not get affected by because of atmospheric factors, but because of heavy clouds or some other reasons may get affected. So, in PSI these effects are minimized. Now, PSI techniques can overcome such limitations by relaxing usual baseline and temporal constraints. So, the conditions of baselines is not that big in persistent scatter, and maximizing the number of usable interferograms, because this issue of coherency, issue of baseline, issue of temporal constraints are minimized in PSI, and then these can be used to calculate the mean trends over the time from a large history of interferograms. So, at least 12, 13, 14 scenes are required to develop a PSI interferometry. So, only the targets with sufficient high coherence are considered in as persistent scatterer, resulting in reduced pixel density. And that way what happens that we get the scatterers, these persistent scatterers within an image or within a study area, maybe just few. Like here, if I take an example of the terrain deformation, which is of a part of Spain, in which a PSI technique has been used, and the maximum subsidence has occurred is about 5 centimeter per year, because it has covered a long time period, and therefore the rate can also be estimated. So, rate here has been estimated with that 5 centimeter per year, the area which are having a red persistent scatter or red pixel, if you wish to call them, are showing, whereas some are having very little or no change are there. Though they are performing as good persistent scatterer or good scatterer, but having here basically no changes. Middle, the green one are showing little changes, the maximum changes are being shown by these red pixels or red dots. So, in that way also over a time period we can estimate the rate of deformation, that may be subsidence or upliftment, does not matter, but rate of deformation can be estimated using persistent scatterer. What are the large applications? Some applications we have already touched, but some we will be also mentioning here. Applications of INSAR technique, DINSAR or PSI, all combined together, and basically geophysical or geodesy, it plays very important role, and that is the studying the ground deformations, and in geologic natural hazards also, that we can employ. I have shown few examples. We can employ SAR interferometry in earthquake related studies or earthquake induced ground deformations. Maybe deformations be due to the volcanoes, or maybe deformation due to landslides or over withdrawal of groundwater. So, lot of deformations which might take place on the part of the land or ground, and those deformations either can be estimated using a pair, or rate of deformation can also be estimated through PSI. Time series analysis of surface deformation, that is through persistent scattering or PSI, the subsidence or structural stability can also be estimated. So, there are many, we hear a lot of things about some monuments are getting deformed or some other thing, or that area is subsiding. Those things can be, those areas can be studied through PSI, and we can say that whether there is a subsidence or upliftment, and if that is there, what is the rate also. And then this SAR interferometry technique overall, whether it is DINSAR or PSI, can also be used to monitor the glacier motion and how glaciers are moving, what is the rate and so on. Of course, the first application of SAR interferometry is for digital elevation modeling. So, driving digital elevation models, one of the best examples is digital elevation models generated using that SRTM mission data and implying the DINSAR technique. So, this list is not really exhaustive, as there can be many applications, and many new applications are still being developed using these techniques and these data sets, because the reason is now data is available, and if I talk about the data, especially the Sentinel-1 data, it is freely available for entire globe, and therefore lot of applications are being developed in this area. So, this brings to the end of this part 2 discussion on SAR interferometry. Thank you very much.